In this lab, the motion data of an oscillating mass attached to a spring was investigated as an example of Newton's laws and the energy principle. We investigated how defining the spring mass system impacts the changes in potential and kinetic energies. After collecting data on the motion in Tracker, the x and y position values were exported to a CSV file. This file was read to create the motion of the red ball in the display window. The plots shown here are the x and y position values over time. These values were used to estimate the period of the oscillation for the mass. The period was estimated using both the x position and y position data. Ideally, the values would be the same. However, because this observed motion is not ideal, we can reason that the disparity is likely caused because of some characteristic of the spring on the molecular level. The spring force in the y direction is slightly stronger than the x direction, making the delta y happen over a shorter amount of time. Using the period calculated from the y positions, the calculated spring constant K was determined to be 7.819 newtons per meter. To calculate the relaxed length of this spring, we use the position data just as the mass was released. At this point, the mass has no velocity, thus the F net is 0 by Newton's second law. From here, we know that the only forces acting in the y direction are the spring force and the gravitational force. So using Newton's second law, we can calculate L naught, as shown here. The qualities of the spring and mass were entered into the code as the initial conditions to create the computational model. The calculated values for the spring's relaxed length and spring constant were calculated and entered into the computational model. When the display window is run, it is clear that there is a disparity between the model ball motion and the observed ball in motion. However, both show a pattern of oscillating motion. Because the values for our spring constant are so small, slight variations will affect the computational model's motion values pretty substantially. Any human error from tracker data collection or approximations of the oscillation could contribute to these disparities. The energy plots show the relationship between the potential energies of the spring and mass, plotted in red and green, and the kinetic energy of the mass, shown in blue. Here it is apparent that the energy principle is satisfied because the total change in energy plotted in yellow is a constant value of 0. This is correct because our system is defined as the spring and the mass and the Earth, so there are no outside forces from the surroundings acting on the system. By the energy principle, we know that there is no work being done, so the delta E is equal to 0.